good evening and welcome to this evening's webinar, IB with TI-Nspire, Probability and Complex Numbers, hosted by Texas Instruments Australia. My name is Rodney Anderson and I'll be your host for this evening's webinar. One of the panellists tonight is Pam Durrance, and as you see there, she's from Wesley College and a very experienced lady and teaching the IB program. And the first panellist for tonight is Bojana Graham, and she's also from Wesley College, and they were just chatting to them just before, and they share the same staff room, so it'll be fun and games in their staff room anyway. So, okay, Bojana, I'd like you to commence with your part of the webinar tonight.
Thank you, Rodney. So what I will start with binomial distribution, and then go to normal and Poisson distribution, and then finish with complex numbers, and Pam will look at discrete continuous distributions and some high-level option stuff. So let's start with an example on binomial distribution. Let's say 75% of your 12 students participate in a spot on a regular basis, and we have 10 random year 12 students interviewed, and we want to do a few things: construct a probability distribution table and draw a probability distribution graph, and then also answer some questions. So if I quickly run through that, that's what we can do, but I will try to show you how we can do those questions from scratch. So if I start on a new spreadsheet, and I will say this is X and that's probability. So we have 10 students, so we need to go from 0 to 1. Since it is a spreadsheet, we can drag those numbers. Sometimes it goes a bit too much, so we don't want those. So up to 10. So in my spreadsheet now I have 10 students. And now if I wish to put the probabilities here, I need to use equals, and then I need to use statistics and distributions, and go to binomial PDF. So we have the number of trials 10, and the probability is 0.75, and we have the X value in our X column. So it shows that now if I press enter, it's asking me whether that's column on variance. Still, I call that it is a variance reference. So I have all the probabilities here filled up. Yeah, that's correct, up to 10. So now we'll try to actually construct a graph. So we need to enter the graph screen, and that's my X here, and this is the probability. So I can go through the screens and see that the mode for this one occurs at 8, since our X was, P was 0.1. What we can also do here, we can enter, if I go back to spreadsheet, what I did one variable statistics. So the reason for that is that I can see what's the mean and what's the standard deviation by using just the X values and probabilities, and that can also later be calculated as I did here. So mean and standard deviation using our formula, which gives us 7.5, and this gives 1.369, which is exactly the same. Now, to find the median, there are various options. We could use binomial CDF, and now I use the least notation, so that will give me the values from 0 to 1, 2, 3, 4, 5, from 0 to here. So that's one way of doing that. So I can scroll through probabilities, and these are pretty small, but if I go here, I can see 0.22, 0.47, 0.76, so that's how we can determine a median using this list. We could also use the cumulative, which I will do in another question. So if we now want to see what happens to the probability distribution graph, if we vary the values of P, we can also make the construction with actually the slider. And the slider can be animated and we can see what happens. And of course, every time you can find the values. So I don't know what happened here. So I will try now to construct this with the slider. So what I have here, I have prepared the list up to 20. Now to do the slider, we need to actually enter the first value. So I say let's start with P.1. So I say it's 0.1 and the calculator now remembers that this is the value. And now I do the same thing. So I go to statistics and distribution and do binomial PDF. This time the number of trials is 20. Now probability of the success is P and my X value is X. If I enter this, I get the initial value because I had the P value prepared. And then if I try to get the graph, something happened here. I go back to my prepared data, something disappeared as it happens. So I might just leave that at the moment and go to another example. So this example is when we are not given P, like some examination question. It's a binomial random variable where the number of trials is 7 and the probability of success in each trial is P. And we know that probability X is 4.15 and we want to find P values. So we need to use the formula and then from here we need to sketch the graph. So it's advised that students actually do the graphical solutions. So we use our formula and then put the probability and find the solutions numerically. So I close that at the moment. And next thing I will look will be some normal distribution. So when we introduce normal distribution, how we can go from a histogram to a normal curve. So I have some scores, let's say, for high-level maths exam, which are listed here. And I can put those scores and create the histogram. And then we have the option here to show normal PDF curve. So what the calculator is doing, it's actually calculating the mean and standard deviation of the values as in the spreadsheet, and then it is trying to fit the normal curve here. And so that's how we can introduce the normal distribution. And now let's see how we can create the normal graphs using the calculator. So I go back to the first screen. So we'll try to plot a normal curve, shade the area under the normal curve, calculate normal probabilities, and have a look at some inverse problems. So this one I sketch in the calculator screen, which has some disadvantages. So you just drew the graph and set up the window, and the syntax is normal PDF, and here I use normal distribution with mean 10 and standard deviation 2. It is a bit trickier to put all those values because we either need to draw vertical lines or put X values on the X-axis, which is still possible to shade the areas and show 1, 2, and 3 standard deviations from the mean. But there is an easier way to use actually the statistics graph. So I'll illustrate how that can be done by looking at the IQ scores, which are normally distributed with mean 100 and standard deviation 15. So if I open a new document and I need to just tell the calculator that I have my x values and probabilities, because otherwise it will not sketch the graph, and then I choose graph and I say I want x here and the probability then. Of course I don't have anything, but we have, if we look analyze, number 4 is plot function, number 8 is plot values, and also shade under function. That's why it is quite nice here. So if I want to plot this graph here, I say normal PDF, as is the syntax, and we put x, and IQ scores has mean 100 and standard deviation 15. And of course we have to adjust window settings. So unfortunately it's not data, so it doesn't adjust by itself. So let's put some values here, and that's a bit of playing around with that. So now we have the normal curve sketch, and we have some values of x and probability. So next thing, we would like to see what happens if we are one standard deviation from the mean. So again, we go menu analyze, and we have plot value. So I can say 100 minus 15, which is one standard deviation below the mean. And if I do the same plot value, but this time I go 100 plus 15, that gives me one standard deviation above the mean. So I have the curve here, one below mean, one above mean. Now, if I go again to menu and analyze, I can shade under the curve between those two values. And I get this area, which I can make different color. So clicking in between, I can see this is one below mean, that's one above mean, and this is 0.68. which gives us the area within one standard deviation from the mean. So if I go back to my normal curve, that was the graph I created. I can create similarly the graph when I have two standard deviations below and above the mean, which gives me the area 0.95. So that's a nice introduction to normal distribution, and drawing it here is probably the easiest way because it doesn't require much, just remembering the syntax for normal PDF, x, and mean and standard deviation. So of course we might answer some other questions. So looking at this example, again looking at IQ scores, how many adults in Australia would you expect to have an IQ above 170? How many above 180? And we want to find IQ scores for the middle 50%. And according to the ABS data from 2014, I check, we can assume that the adult population is about 20 million. So we need to use normal CDF, which on normal screen is also in probability distributions. So if we do that, we get this value, and multiplying by 20 million gives us about 30 Australians. Now if we go over 180, the probability, as we can see, is quite small, and then we would only expect about 1%. If we want 50%, these are the questions where IB studies are asked on the exam, because they only ask questions where mean and standard deviation are known. So we need to find inverse normal, between 0.25 and 75. It's in other words, it's the IQR, so we can get those two values using just inverse normal. It can also be illustrated, so what I've done here, I split the screen and I still have those two values, Q1 and Q3, and then I have drawn that and it shows that the area is 0.5, so that just enhances the understanding between the graph and the calculations. And it's always advisable to the students to sketch the normal curve and shade some areas because clearly it is very helpful in their calculations.
Yes, but Jan, I'm just looking at there, like most participants, it's very effective seeing the split screen and seeing the actual answers there to your calculations.
Yeah.
It's very great visual, isn't it?
So next question I will look at is normal distribution problems when either mean or standard deviations are unknown. So that will be more for standard level and high level students because studies always know those two values. So let's consider the random variable x, which follows normal distribution with mean 20 and standard deviation unknown, and we know that this probability is known. So what I'm trying to show here is again the effective use of the calculator. So we know greater than 19, so inverse normal always goes left to the point, so we need to actually calculate 0.3. And it is good for the students to store this value for later use, and store is you just use control store, and we can store it as a pronumeral, because then we can use that using numerical solve without the necessity to rewriting the variable. And that is the most accurate value we can get, which gives us the standard deviation 1.91, because that's three significant figures for our IB courses. And going back, so this is the question, and here I also illustrated that on the split screen. Now, this time I have actually drawn the standard normal distribution showing 0.3 and 0.7 here and referring to the standard normal distribution graph. One more example is when we have the masses of boxes of apples are normally distributed, and we know 20% weigh more than 5 kilograms and 15% more than 5.6, and we wish to estimate the mean and standard deviation of the boxes. So again, we use inverse normal, but what I'm trying to show here is that we can store the values. So inverse normal 0.8, and we store that as Z1. So of course it's standard normal distribution. We need the Z values corresponding to our X values 5 and 5.6. We do another one here and also store it as Z2. And then we can use linear solve, which is in algebra, and solve system of linear equations. So that's where it sits. The funny thing here is that actually using Z equals X minus mean on standard deviation as a fraction doesn't work with linear solve. It has to be rewritten as Z1 times D. You can't have Z1 5 minus M on D. It says that it's not linear, so that's probably something worth noting. That's what I put the note over there, and that gives us the answer for the mean and standard deviation here. So I close those two, close some so it's easier for me. So I have a look at some of the complex numbers, calculations and operations on the calculator. I like this joke. The number you have dialed is imaginary. Please rotate your phone 90 degrees and try again. Probably at the start students wouldn't understand what's that about, but after a while they would. So what happens with complex numbers? Of course, we can do various operations here. And what I'm displaying here is different settings on a calculator. So I might have 1 plus I in Cartesian form, which is called rectangular on the calculator. I can display it in Euler form, which is equivalent to modulus-argument form in IB. And this is the setting in radians, and I can also change this setting to degrees. So if I actually put a new calculator screen, I can illustrate how that can be achieved. So if I go 1 plus, and now we need to use I from here, not just a letter. So because my calculator now is in degrees mode, and also if I go to settings, document settings, we have various forms. So I can have real or complex, and complex comes in 2 forms. It comes in rectangular form or it comes in polar form, and that will affect the display. And angle, of course, can be in radians or degrees. Definitely it's recommended that all the answers, they have to be given in radians, but sometimes for the students it is easier to see what happens if we try to have actually things displayed in degrees, and then they can recalculate to radians. So that is just an idea. So if I change my settings back to radian, and now I will change to rectangular, then I can perform some other calculations. Very useful feature is polynomial tools, and we do find complex roots of the polynomial. So let's do a couple of examples. So if I go z squared plus 9 and comma z, and now I'm in rectangular form, so it will display the roots. We can just do a couple more, and that's a nice thing to illustrate the conjugate root theorem, looking how many roots we have each time and showing that complex roots occur in conjugate pairs. So if I change that, so I have again minus 1 minus, here minus 1 plus, and we get 1 real and 2 complex, which occur in conjugate pairs. And of course we might try a few examples like that, and the students can see what happens to real, to complex, conjugate pairs, and so on. I will do one more, and from here I will try to illustrate how we can actually sketch that on the complex plane. So let's say if I have z cubed minus 1, I get those values. So what I want to show, how we can actually show the nth roots of a complex number by displaying it on the complex plane. So I displayed 5th root of I here, and 6th root of minus 4i, and 5th root of I, and so on. So if I go to this document, and we look again at z cubed minus 1 equals 0, which is equivalent to z cubed is 1. Now what if we want to find z numbers such that they are cubed roots of 1? So we use, of course, the Moivre's theorem, and we arrive at r equals 1 and theta is 2k pi on 3, where k is 0, 1 to 2. So if I want actually to display those roots, so I show how that can be done. So we need to go to the calculator screen, and we need to change graph entry to polar. So for our cube roots, we have r equals 1. We started the initial value 0. So what we are changing here, we are actually changing here the step, which is 2 pi pi, not I, 2 pi, and we divide the step by 3. Of course, if I draw it this way, I just get a circle. So I will zoom in a bit. Doesn't matter that the shape is a bit dodgy, not quite a circle. So now if I right-click and the student's control menu and go to attributes, and if I go to here and change the graph to discrete, what I achieve by doing that, I get the actual cube roots as I've shown. So if I want to find other roots, of course, fifth root I would divide 2 pi on 5, but the first one is the root which the students actually need to calculate. So it's a good class activity to set, let's say, maybe a few groups and each tries to find something. Fifth root or sixth root of particular complex number using the Moivre's theorem and going through the calculations, and then they need to have the exact the values to actually display those roots so they can be seen. So of course sometimes the radius will be different. So that's how the nth roots of complex numbers can be displayed. So some other things we can do, we can actually find real and imaginary numbers, which if we go to number and complex numbers tools, we have complex conjugate, real part, imaginary, polar, angle, magnitude, and that's the way to convert between the forms, not just changing the settings. So these are a few other options we can have. So that's what I did here, and that's a little spreadsheet where the students can fill in real, imaginary, and actually find what they are as the initial activities. But if you are more operations like division of complex numbers, the calculator will do it easily. We can also, that's a spreadsheet which shows the values, so students can play with that and change that. If they go, let's say, -6, then they will see when a particular number goes. So that's a few more things they can do. That's again using the angle and modulus of a particular complex number feature as I shown, and there is some more theory here. Maybe important thing is to mention that the Euler number is displayed on a calculator like 4e to I theta or something, should be r, not the modulus argument form, so the students need to be aware that those forms are actually equivalent. So it's 7:30, so there is one more thing on quickly show the Poisson distribution. So similarly as I did with the binomial distribution, we can also look at the Poisson distribution. So I have the Poisson distribution with mean 2, and here I sketch the PDF values. Now we can also get in the spreadsheet cumulative values by just taking this one plus B2 and scrolling down. So that will allow us to find the one with the highest probabilities, which is bimodal here because they are the same, and the median value from the table. So I think I will stop here, and thank you very much for your attention, and I pass on to Pam now.
Thank you, Božena. It's a great start to the evening. So you demonstrated a lot of applications and how to demonstrate the complex numbers and change the settings. So it's very useful.
Thank you.
As Pam is setting up here. Oh, we can see your screen now, Pam.
That's terrific. Hopefully you can hear me too.
Yep.
Okay. Well, following on from Božena, So I was going to look at some of the probability distributions that come up in both standard level and high level courses. So I wanted to start off firstly with the discrete probability distribution, which appears in both courses. And a process that you may not have been using is the spreadsheet application. So I have, which are all attached in the files when you download them, I just have a couple of examples here. So this discrete distribution, it's a typical exam style question where you may have to find a missing value for a probability, or it may be that all of those values are in terms of k and the students need to solve that. Obviously we can't do solve on the non-CAS, but we can use numeric solve, but I'm going to skip through that because that's another webinar. But the value of k in this case is 1/3 or 5/15. So the next thing is to have a look at how we can determine that expected value, because that's where the calculator can be very useful. So I've actually entered those values 0, 1, 2, 3 and 4 in, I've called that particular list the X value list, and then I've put in those associated probabilities. Notice I've slotted in the 1/3 there. So with finding the stat calculations, one of the things that is very useful is the one variable statistics. I've got just the one list, which is my X value, but my frequency is the probability, and that's going to pop that into result column D. So if we have a look over there, what we actually see, if I just move across a little bit, okay, oops, too far, there we go. So we get a whole list of these statistics that have been calculated on that data set for us. Now, we've of course used all of these in statistics, but with the probability distribution, what we see happen is the X bar and the sum of the X values is actually the expected value. So either of those can be used as the expected value. The sum of the X squared value is our E of X squared that is required in some parts of the exam question. Our sigma is of course our standard deviation there, but if you scroll right down to the bottom, we get this SSX, the sum of the square of the deviations, and that 1.9733 is in fact the variance of X. So when we're asked for the expected value and the variance, we can get that quite quickly from the spreadsheet. So just keep in mind that with a probability distribution, that is our variance there. You can of course also get that from, oops, there it is, squaring the standard deviation. So both of those give that to us. And as I said, these are both our expected values. So I've summarised that on the next screen so that you'll have that there for your records. Okay, so with discrete distributions in the two courses, binomial turns up in both standard level and high level, and the Poisson distribution, as Jen has already said, was also in the high level course. And then in the high level option, if you happen to choose the probability and statistics option, there is the geometric and the negative binomial distributions. So as with the binomial distribution, which Jen has shown us quite a few things, the Poisson and the geometric distributions are both included within the probability menu on the Nspire calculator. However, the negative binomial needs to be done with the aid of the formula associated with that distribution. And that's located in the formula booklet for high level. So what I've done here is actually just defined a few things. So I've defined a sequence. These are my X's. And they're just the numbers from 0 to 20. And then I've said, well, my first Y's are going to be those X values of the Poisson distribution for an average rate of 1. And I've done that a few times, but I'm saving a little bit of time here. But I've done that for the first 5 values there, so changing the average rate so that we can see what happens. So what I've got here is a scatter plot on the graph function page. So it's this graph function page, and I've created in the menu, in the graph entry, I've gone to scatter plot, and it pops up with that menu there. So I'll just flip back. So this is the first one where the average rate of the Poisson distribution was 1, and we can see that those values go on. There's not really much excitement happening after x equals 10 because all the values are quite small at that point. But what I do like with this as a teaching tool is that you can then put in the x's, and this time I'll put in the y2 values. So what we can see is the change in the shape at this point. So we can see that when the average rate was 1, that the 0 and the 1 were basically the mode values. But now that we're getting the average rate being 2, that mode has changed to 1 and 2. And so if I just get that up, I can do the next one. And you can see very quickly that we start to get a closer distribution to a normal curve, which is why if you do the probability and statistics option, that we're able to make that approximation with some Poisson distributions to a normal curve. So just, I'll quickly put those others in. And you can see the much more symmetric nature of those graphs with each one I put in. And that one, for the first 10 values, looks very much symmetrical. And you can, of course, do a graph trace on those and find particular values. So it's gone to this value here. If I just press the up button, I can go to those same values on each of the curves. And in each time, that first value is, of course, the x value at that point there. So, and that's the probability associated with that. Okay, skipping through that one. So the other place I can show this is actually on a data and statistics page. So if I put the x's here, naturally they were just the numbers 0 to 20, so that's a nice even spread. But I'll just go to the average rate being 3, and I can once again generate that Poisson PDF. So there are two ways that we can do that. So we can do the scatter plot within the graph entry and also on a data and statistics page. The data and statistics page is really nice because you can just put your cursor over the particular points and you can find the probability of x being 3 for that value is 0.224, etc. But we can also analyse and do a graph trace, and then we can type in the actual number. So if I want to do 2, no, that didn't pop up, sorry, I'll just escape from that. But you can, I'll give it one more go. No, not working for me tonight. Virginia and I are both having difficulties. Okay, we'll move along, but you can, of course, just highlight the particular values. And you can see that the probabilities get very small very quickly. One of the things I found with some students, when they click on some of these values, they go, oh yes, that's 1.27. Of course, you can't have a probability of 1.27, but they ignore the fact that at the end of that, there's actually e to the minus 5, so it's actually a very, very small number. So it is something to keep in mind that the students do look at the whole number. Okay, so moving along, the other thing that we can do with the Poisson is actually enter that Poisson PDF into our screen. So doing that, if I just type in Poisson PDF, you'll notice that once I hit this F, it'll go to non-italic because it recognises that's a function that the calculator can do. And once again, I'll do for an average rate of 3. Now I'm going to press enter, and you're going to be thoroughly underwhelmed by that because you don't see a thing. And unfortunately, it doesn't show up on that. But if I do Control T, what does come up is the table of values. So if you want to generate a table of values of that, you can do that from a graph screen, and we have those values there. So the probability that x equals 0 is 0.049, etc. The probability that x equals 1, the probability x equals 2. And then once again, as we get down here, we can see that those values are getting very small, and you'll notice those e to the minus 4 bits coming up at the end to show us that those are very small probabilities. So I'll just get rid of the table. So Control T or Control Z will undo that. And what I'm now going to do is enter the Poisson CDF. And once again, once I get to that F, it changes because it understands that, for also 3 to X. And this time we can see that graph, but what we can see is that it's discrete until it's virtually almost reached 1 at this point. So now when I've got those two functions there, if I go Control T, you'll see both parts within the table. So we can see those values there, and at the same time we can see the cumulative value increasing. So for those questions where we want to know whether it's at least a probability of 0.5, then we can say, well, x equals 2 won't be enough, but x equals 3 would do that. So we can answer those types of questions. Okay, so moving on. As Virginia said, the Poisson distribution comes up quite a bit in the high-level course, and typically there are two types of distinctions that the examiners try to make where the students understand the difference between finding the probability at a particular x value or finding a probability up to a particular x value. So we use the PDF or the CDF, and sometimes within those questions, depending on how many marks are associated with it, then there may be a change in the mean to be used. And then if it's a more difficult question, sometimes they have to solve an appropriate equation to determine an unknown mean. So I'll just click back over here. So I have just a standard question so that you can see how we use the Poisson PDF and CDF. So given the average rate of phone calls is 1.8 per 15 minutes, determine the probability of receiving exactly 3 calls in the, that should be the next 15 minutes, or more than 3 calls in the next 15 minutes. So we can do that. I'll just skip across. So it's the probability distributions, and the Poisson is actually at the end of the road there. So we want the Poisson PDF in the first case. The rate was 1.8, and the X value that we wanted was exactly 3 phone calls, and so we get the probability of 0.161 to 3 significant figures. The other, the next one was more than 3 calls in the next 15 minutes. Well, with all of the distributions, they all do up to and including, but they don't do greater than. So it's something to keep in mind. So if we want more than, then we actually want 1 minus the probability of x less than or equal to 3. So we can put in the Poisson CDF, which is in the same menu, probability distribution. And if you go up on the calculator, that's the first one you get. So the Poisson CDF, the rate was 1.8. The lower bound, because we're subtracting up to and including, we'll leave that at 0, but you can alter that depending on what you are finding, and the upper bound, because it was more than 3, we want to include the 3 in what we want to take away. And so that will do the calculation very simply for you. Okay, so in the high-level course, the other thing that is required is the continuous probability distributions, and these are often given in this way. As part of the high-level option, there is the cumulative density functions as well, which are also given similarly to this, but usually with the uppercase F to denote that it's an integral. So, for the continuous probability distribution, here I've got a fairly standard one, 4 on 27, x minus 2 squared, 5 minus x, where x is between 2 and 5, and it's 0 otherwise. So I've defined that, that's f of x. So the types of things that are required to be found are the mode, which is the x value of the maximum on the graph. So this is something we've seen through the examinations. Lots of students can find that maximum point, but they often don't know whether they should be giving the x value or the y value. So it's really important that you do stress that it is the x value. For the median, or any of the percentiles, and sometimes they have been known to be asked to find the interquartile range, so you would need Q1 and Q3. But for any percentile, what we're solving for is an area. And then the mean, well, that's given to them in their formula booklet as the integral from negative infinity to infinity of xf of x. And then the variance, which the simplest form often on the calculator is to do this calculation. So let's have a look first of all at f of x. Oops, what's that one? Control G. So if I put in f of x, notice that that's gone bold because I've already defined it. And no, got that. So here it is here, and we can see that it is defined just between 2 and 5 there, the curved part, and it's 0 elsewhere. So to find that mode, it's just a matter of using analyze graph, and we can find the maximum. So you click to the left, click to the right, and there it is there. And we can see that the mode occurs when x equals 4. I just go across here. What I would now do is find the median. So I'm going to use the menu algebra numeric solve because there is only one median. So nsolve is great when you know there's only one solution to be found. But here's an interesting thing that happens with the solving. If I call this m, and I'll put in here f of x, which it knows that's there, and I'm going to solve that for m. So, oh, sorry, need to put in equals 0.5. There we go. If I do this now, I'm going to get an error. And the reason why that is because it doesn't know whether to go forwards or backwards from 2 to try and solve that. And of course, if it goes backwards from 2, it's not going to get anything. So it's in a bit of a dilemma. So we help the calculator out by saying, well, no, we only want values where m is greater than 2. And there it is, and it's very happy. It puts up the warning sign just to let you know that, well, it was a bit confused to begin with, but now it's all happy with that. So when you're solving for a median, or if it were the first quartile, you'd let that equal 0.25 and so on. We can also do the mean and the standard, the variance. So the mean is always over the complete x values that are defined for that function. This time I don't need to put in anything to tell it not to, to be greater than a particular value because I'm only putting in the values of 2 to 5. But I do need to tell it to multiply that by x. And so I find the mean as 3.8. And if I wanted to do the variance, 2, 5, then I need x squared times f of x, x, and I need to take away, let me get out of that, the mean squared. And so I find the variance is 0.36, and I can take the square root of that to get the standard deviation. Right, so one of the things that also comes up in the option is the expectation algebra. So a little activity that I like to use with starting out on that is the rolling a die. So I have a little template here that you'll be able to run off for your students, so you can put in the x values that are possible on the uppermost face of a die and the probabilities of that. If they were to double their scores, so you would put in 2, 4, 6, etc. And then if you were to roll a die twice and add the scores, then the results would of course be the numbers 2 through 12. So what I've done is set up 3 spreadsheets, one with the single die and the probability of each of those values happening, doubling the score, and the probability of each of those happening is still 1/6, and then the sum of 2 die, so you've got that going up to 12 and the associated probabilities. So a nice activity to get a familiarity with that expectation algebra is to do the one variable statistics. Sorry, I clicked too quickly. There we are. And once again, we can do the one list. Here I'm going to put in the one die and the probability of one die. And I get that, and I can see straight away that the mean is 3.5. And because it's the probability, I can just go down here to the bottom and see that the variance is 2.92. If I then do that again, so menu 6, 1, 1, but this time put in the double and the probability of double, I can see that my mean is 7, but my variance is now 11.67, which is exactly 4 times the previous one. And one more time, if I do that, if I put in the sum of 2 values and the probability of those 2 values, what I can see this time is that the mean is still 7, so it has still doubled, but the variance is 5.833. And the reason why that is because, of course, it is the sum of 2 independent x values as opposed to the doubling of the x values. So there's that nice difference there. Now, we're just about out of time, and I was going to talk to you about type 2 errors, but if you have a look at my completed document, you will be able to see some of that. The type 2 errors is the more difficult error calculation that the students have in doing those ones, so the probability of accepting H0 given H0 is false. So I have set up a little example there which you'll be able to have a look through, and I've put the graphs both there. Notice here that the standard deviations are in fact a half, and that's because there were a number of samples with 4, so we need to divide the variance by that. So that's why the standard deviation then becomes 1/2. When we have a number of samples, it is the same process as if we have a sample of a particular size. So they both get divided in that case. Anyway, I think I better stop there so that there's a bit of time for Rodney to close up. But thank you very much for your attention.
Yeah, thank you, Pam. like in my classes, that time flies when you're having fun. I was thoroughly enjoying that tonight. You and Bojana, we could keep them going for a lot longer, but we are limited with the time at times, aren't we? So just summing up, if you actually head to the Texas Instruments Australia website, and you'll see the webinars, we'll look at it shortly, but I want to show you today regarding the Teachers tab. So obviously, and through there you'll see a number of menu items. So you'll see that you'll find activities and assessment items aligned to the Australian curriculum. So if you click on the Australian curriculum inspired, and you'll see the various year levels and the strands and many resources linked there. So you've got TNS files, PDF, Word documents, Navigator files. So we keep on going down there. So senior curriculum, you'll see the same thing, resources relevant for states, and more states are being added to the lists and extra resources. And as up here in Queensland, we still use those files from Victoria, New South Wales and ACT. So we all share resources, and teachers write these files and the resources for teachers to share. Then the TI codes. Teach yourself programming in 10-minute steps. So you've got the programming modules for TI-84 and the TI-Nspire. So, and you follow the particular calculator and just click on the lessons and away you go. And then teacher resources, it just doesn't stop. And you'll actually see the resource you can actually think of professional development. But wait, there's more. We haven't heard that ad for a while. So the Learning Centre, and search for activities and other resources. So you select what calculator you've got or software, and you'll see the Science Inspired, the IB Aligned, was Bojana and Pam were looking at tonight, and there's other webinars and tutorials, and keeps on going, professional development. And there you've got the newsletter subscription. And back to the home page, you'll see the webinar section. So if we click on that there, let's have a look. And you'll see two tabs, the upcoming webinars. So you saw tonight's wonderful webinar from Bojana and Pam. And as coming up on this Monday, you've got Melissa, John and Jim talking about which graphing calculator is right for your school. And many more as the year progresses. And then on the demand, so in a few days' time, you'll actually see the recorded webinar and the many TNS files that Bojana and Pam actually shared with you. There's lots there. I've seen them. And you'll see there's so many there. If you've missed a webinar through the year and previous years, it's all there. So, okay, so wrapping up there. So thank you, Pam.
A pleasure, Rodney.
Thank you, Bojana.
Thank you very much.
So good evening, and we look forward to you participating in future webinars. Bye for now.